Okay, so in this video we're going to be doing what's called kind of a constraint analysis for buildability based on terrain and a few other factors for where you could site solar panels. And I only started doing this type of work in the past year or so. And when I first met the guy, this is an example of a product that I make for a client. And when I first started meeting with this guy, I told him that with GIS we do have the ability to calculate or estimate rather the potential solar irradiation, kilowatt hours per square meter or something like that, so that you could actually kind of get a good estimate of how profitable it would be. And he said, it's really not even that complicated. Like from his perspective as a developer, he just wants to know how many potential acres are even buildable for certain parcels. And I think for that they have to look at distance to three-phase power and a whole bunch of things like that. So anyway, the terrain is really just the biggest constraint for is something developable. In general, if something is over 20% slope, you can't really develop on it. And for solar, because we're in the northern hemisphere, if it angles to the north or if it angles to the a different direction, then there are different set types of slopes, different kind of gradients of slopes that he deemed acceptable or unacceptable. And so we're going to use kind of a modified version of that, of aspect, which is that direction of slope, and slope gradient to kind of come up with our general buildability analysis. And, I think in practical terms, there are places where, with little pockmarks like this, they might be able to make some of that stuff work. But just for a baseline, it's nice to be able to see the buildability as a layer. And so what we're going to do is we're going to take a DEM, we're going to create a slope raster, we're going to create an aspect raster, then we're going to create definitions from those that create binary layers, meaning zeros and ones, and we're going to intersect those so that we can see if, where based on these definitions something is okay or it's not okay. And so ultimately this whole layer right here, this green layer, would end up being a 0 if it wasn't buildable, or a 1 if it was buildable. And there are other definitions too that we're going to take into account. For instance, you can't build on water. You can't build in near a wetland. Certain types of wetlands, there's a setback, kind of a Euclidean setback that you have to take into account most places in, at least in the Northeast. And then there's flood zones as well that you're not supposed to build in. So anyway, this is kind of an example. The terrain is one thing. We're also going to be looking at, other types of things like land cover, right? This particular client doesn't really care too much about land cover for the first cut, kind of the first analysis, but clearly it's easier to build somewhere where there are no trees rather than having to clear land. So what I usually provide this client is the site analysis on a topographic map, so you can get a sense of the slope, and also an aerial map, just so you can get a visual sense of what's clear and what's not clear. So without further ado, well, actually, this is interesting, right? There's a polygon here that's classified as a wetland, but in this state, we've worked in a few states with him, Mass and Maine and Virginia, and in Maine, this is considered a forested wetland, and it's under a certain size, and therefore it's not protected. And wetland data tends to be a little wonky, at least in Maine. You might walk around here and it might not seem like a wetland, but it's based on some national definition with kind of coarse data sets. And so a lot of these blobs appear, and then when you go out with a landowner, you find that, oh, well, yeah, it's a little soggy, but it's really just based on some kind of analysis that they did at a high level, and it's not actually there. Whereas a lot of these bigger blobs really are, you can kind of see there's a perennial stream here. It becomes clearer with larger objects that, yes, this is a thing. And so the zoning, they're called overlay zones. When you look at each town usually has some kind of overlay zone or district where it's shoreland zoning, how far back from the edge of either a wetland or a water body do you need to be. There's other kinds of overlay zones as well, but we're going to be dealing with wetland setbacks this time. So let's get into GIS and see how we can start making these definitions. All right, as usual, I'm going to go and save. I'm going to save under tutorial C and call this constraint analysis. A lot of times I'll have multiple QGIS documents for different purposes. You know, if I want to have kind of different canvases in which I can play. So the first thing I want to do, I'm going to go to my project home, and let's just take a look at this land cover data set. So for terrain, you should have these two. There's a land cover data set, and there's a digital terrain model with the vertical units are meters, and it's in EPSG-32145, which is a Vermont State Plane system, I believe. So I'm going to pick Vermont. Let's see, which one do I want? Let's just do, doesn't really matter. I think that one's fine. Let's do it. Okay, so this is a land cover data set, which you've seen this already before, but this one doesn't come with a palette. It's resampled from a Vermont-wide, very, very detailed, very nice 2016 land cover data set. I think it's 1.5 meters. But this one's been resampled to 10 meters so that it will match up perfectly with our elevation model. Because our elevation model, if we kind of get these to line up perfectly so that each cell lines up with each cell, then we can use the raster calculator to kind of do different kind of calculations between these data sets, and we're going to derive a lot of data from just these two data sets. So I think the first thing I want to do is just actually give these land classes color so that I can think about them more easily. It looks like there's only 8 classes. This is an integer raster. So I'm going to go look at the metadata for this and then just quickly color this land cover data set so it makes more sense to me. Yeah, just go and open up your tutorial C, and under resources you'll find land cover base and then this is the a text document, and this text document will have if you scroll way down here we go. Here's our kind of enumerated domain. Here's what everything means. So it looks like 1 is tree canopy, 2 is grass shrub, 3 is bare soil, and so on. So let's open up this guy, and I'm going to go to my properties here, and the easiest way to do this is to go to your symbology and paletted unique values, and if we do that we can say classify, and it gives us kind of the 8 classes, and if I hit apply, of course it's gonna do something weird like that. But let's do 1 is tree canopy, so let's make that some kind of green, maybe a dark green. And 2 is grass shrub. Let's make that yellow, perhaps. And I'm just going to do this really quick. And 8, railroad. Let's make railroad brown. So I'm just kind of flying through here. I know it's probably faster than you can follow, but I'm going to do that. I hit OK. So now we've got something that looks a little closer to a land cover raster, at least visually. Same data, but just visually looks a little better. So there are a lot of definitions we could do. I think the simplest one for this constraints is to just say, no, we can't build on the water because we can't. And yes, we can build anywhere else technically. For later in the lab, or later next week, we'll look at maybe where should we build, for Monday. But for now, I want the constraints to just say it's impossible to build on the water. But otherwise, technically we could clear land, and technically we could bulldoze existing structures or pavement or buildings. So we'll do 0 and 1. So the easiest way to do this is in Raster Calculator. So go ahead and open up Raster Calculator. And it kind of seems intimidating at first, but this is actually a really useful, really slick tool that lets you do a lot of cool stuff. And so we see our rasters pop up in here, and it says at 1. And what that means is that this is a single band raster. So a band is just kind of a raster layer. With anything that's a red, green, blue image, like an aerial image, there will be multiple bands. So there'd be if we had an aerial image here, which was red, green, blue, it would say, aerial at 1, aerial at 2, aerial at 3. So you could do different things with those bands. But for almost all of what we're going to be doing in kind of GIS world is just dealing with a single band layer. So if I want to just make a definition where I say give me the water, I could say land cover equals, we know water to be 4. So if I say that, it's going to say, yep, the expression is valid. And what it's going to return to me is a boolean raster, something that's a 0 where it says, no, that's not true, and something that says 1 where, yes, that is true. So let's just see what we get here. So I'm going to go back to my tutorial C folder, my data, my terrain, and I'm going to say water. And if I say save, and say OK. And so there you go. There's the water. You can kind of see 0 is no, 1 is yes, water, no water. But what we really want is we want everywhere except water, right? So if we want everywhere that's not water to be a 1, and we want water to be a 0, because when we end up doing our intersect later, we're going to be doing these binary things where we multiply 1s times 1s equal 1s and 1 times 0 equals 0, so that we can kind of cut out things that we don't want. So how do we get the opposite of that? Well, it's not too hard. We just say we want land cover, and we could say where land cover equals 1, like this, because land cover equals 1 is forest. Or land cover, and then we could go down the line, equals 2, or, and we can do that for every single class. So or is a statement that lets this be true or this be true. There's another statement called and, which you hopefully you've heard of before. And would require both of these things to be true. And it's telling me that this is invalid because something can't be 1 and 2. In this raster, every pixel is either 1 or 2 or 3 or 4 or 5. So I could build a really long statement and just exclude 4, but there's kind of an easier way to do it. The easier way to do it is to say, where does the land cover not equal 4, right? So that expression is valid. I'm now querying this raster and saying, I want every pixel in this raster that does not equal 4. And now it's going to return, I think it's going to return, it should, the inverse. So I'm going to say, I'm going to call this not water. Maybe I should put a little hyphen in there. Okay. So that seems pretty good. I say OK. And boom, there, I've got the inverse. So what this is going to do is, with future things, these zeros will help us cut out places that are unbuildable. So that's pretty good. I'm going to actually get rid of these now, because I think I've done all I want to do with my land cover data set at the moment. Although, you know what I'm going to do is I'll remove these, and I don't want to lose my symbology here. So I'm just going to leave it there, and I'll talk about how you can save paletted symbology at another time. So the next thing I want to do is create an aspect raster and a slope raster. And we can derive both of these from a DEM quite easily. You should know what these are now from the quiz last week and from a couple videos. The important thing when running terrain tools is that your X and Y units, which are the units that define the pixel, the width and the height of the pixel, should be the same unit as the vertical unit. And so the vertical unit is meters, right? This is 0 to some max, around, I don't know, 1,000 and a bit meters high for the Green Mountains here. And then it's probably not 0 because it's Lake Champlain, it's not the ocean, but some minimum that's near that. And I've gotten to the habit of calling things, at my business, we have a very strict way of talking about DEMs. And it's kind of different everywhere, and I'm sure Bill has had a lot of experience with different nomenclatures over the years. But a DEM is a very general term that just means digital elevation model, right? There are different kinds. There's elevation models that show the bare earth. There's elevation models that show the canopy, for instance, like the tops of the trees. There's elevation models that show the surface, so it might show the bare earth, but also the buildings, and then not the tree canopy. And so, at least for me, anything that shows bare earth, I call a DTM, which is a digital terrain model. and things that cover the canopy are digital canopy models, and then anything that does the surface is a digital surface model. That's just what I've decided. It's not, I don't think it's, set in stone or anything, but when I call things DTM, you should just know that I mean it's a bare earth elevation model. Okay, sorry, I had to fix something, so we're all set, but let's go ahead. I lost my land cover and my palette, but that's fine. Let's go ahead and just run the slope tool, because I think that one's an easier one to wrap our brains around for a second. And I think at this point slope should be pretty obvious. It's the gradient that we're trying to measure from this elevation model, so it kind of tells us how steep something is. And this default tool for Q isn't bad. It calculates it as an angle, kind of in degrees, which for science-oriented things is great. Most people, most builders and site analysts I know, though, they like percent gradient instead. So if we did this in degrees, we'd have to run it through the Raster Calculator and kind of run a transformation on the slope to get percent. And the reason they like percent is because on a lot of these old maps that used to do it by hand, you can actually, if it's to scale, you can measure distance perpendicularly to contours and kind of count the contours in the distance and get a rise over run. And that's why the percent is really just kind of a ratio. 100% is the same number of units over and up, which would be a 45-degree angle. So anyway, yeah, it's interesting, but we're going to do percent because that's how a lot of these site analysts like to think. So the 20% slope is kind of a standard in the US for being too steep. So this GEOG slope tool I find to be actually a little more useful. So you can find that in your processing toolbox if you can't find it up here. I think, yeah, you can find it here too, I guess, slope right there. I like the processing toolbox though, because it lets you see which kind of engine or which group of tools you're using here. So we get our DTM vertical meters are vertical units are meters, and we know it's in the EPSG 32145, and we know it's meters to meters, so 1 to 1. And we're going to calculate slope instead of degrees. Sorry, we're going to calculate slope in percent instead of degrees. And so what I'm going to do now is save this as slope. I'm going to say run. And great. So what we've got is a slope raster that's hard to see because it's just black to white by default. So what I've given you actually in your 04 resources folder is a prefabricated palette just so that you can kind of see the slope a little better. So if you want to use that palette, what you can do is go to properties and go to, how do we do it here? I think we go single band pseudo color. Yep. And then we're going to go to this file right here, load color map from file. And then we need to navigate to our resources folder and take slope classes and go open. And see, what I've done is kind of created this classification scheme. So we know this is a continuous raster, right? Every pixel is a decimal point. Each one individually records to a certain number of significant digits what its individual slope is. But I still think it's easier to look at it classified instead of as a gradient. So we hit apply, and now we can see all of the places where the slope is less than 5%, 5 to 10%, 10 to 15%, 15 to 20%, and so on, and over 30. And so it's kind of ugly to look at, but at least it provides a little bit of a sense for where things are too steep to build, which obviously in the mountains is going to look really a little crazy. So we did the slope. That's great. This is ready to be used for different definitions. The next thing I want to do is create an aspect raster. And in this case, even though there's a GEOG aspect, it's actually a fine tool, but I kind of like this one, the default Q tool, just because it's so simple, and aspect is kind of a simple thing. It's just telling us what direction the slope is pointing. So I'm going to use this Q aspect, and save it as aspect. We're going to hit run. And this is also confusing to look at. It kind of looks like a hillshade, which it's not at all, so be careful. And I also gave you a prefabricated color design for this as well. So I'm going to go and open up the single band pseudo color and go back to this load color map and aspect classes. And this is actually not a set of classes. This is actually a gradient. And I'll show you what it's going to do here. I'm going to hit apply. We're going to say OK. And this crazy looking thing is telling us the direction, right? So this is also a continuous raster where every pixel is recording a unique value from 0, which is north, to 90, which is east, to 180, which is south, 270, which is west, and back to 360. So 360 and 0 are both directly north. And I use this because it's it's really crazy to look at, but it's helpful in the sense that if you kind of put these colors on opposing sides, you can kind of start to get a sense of the northern places are all red and the southern places are all kind of this cool cyan. So now what do we do, right? We've got our aspect and our slope, and we want to come up with a definition between these two things for what's acceptable and what's not acceptable to build. And so I actually find when trying to come up with definitions like this, it's helpful to look at diagrams or just draw it out, draw out what you're trying to say. So I actually did that for this particular problem. And the first thing I realized was that when talking with people, they think more in terms of cardinal directions than, radial degrees. But the raster itself is in radial degrees, right? It's in 0, 90, 180, 360. But the client wanted to talk in terms of north, south, east, west, northeast, and that kind of thing. And so what we did was came up with a definition that said north was everything. We just took those directions and then split kind of like a circle, a radial circle, into 8 pieces. So everything north was really everything kind of equally from where northwest stopped and north began. And so we kind of came up with these specific class breaks for what was defined as north, and northeast was everything, from there to there. I guess they're what is it? Yeah, it's 180 divided by 4, so whatever that is. And so yeah, once we did this, it was easier to talk then about, well, let's have northwest, north, and northeast be north, and then all of these other directions are kind of more acceptable. And so the definitions that we're going to use, at least for this project, is that anything that's facing north because it's facing away from the sun, the slope cannot be steeper than 10 degrees. So anything under 10% that faces north is okay. But everything else, so long as it's not greater than 20%, is also okay. So what we have to do from this is we have to come up with a way of saying, making a statement that says, when the slope is greater than 20%, as well as facing these directions, then it cannot happen. And a slope that is less than 20% and facing these directions, it can happen. And then similarly, up here we want to say anything that's facing north and less than 10% can happen, but anything facing north and greater than 10% cannot happen. So it's kind of confusing, but in Raster Calculator, it's a little simpler than it might seem. So let's go back to Raster Calculator and see if we can come up with that definition. All right. So, you might be thinking, well, could we just create a bunch of binaries and do things with them between the aspect and the slope? And you definitely could. But by doing that, you'd run the tool once, twice, and then three, 4 times to get them all to interact, and then maybe even a 5th time to unify them. And so what's cool about Raster Calculator is that you can kind of do all of it at once. So we'll open up this and instead of just like doing one piece and one piece and one piece at a time, we're going to try to write one statement that means exactly what we mean for everything. So if you're not familiar with kind of and or statements, it might be a good thing to review in some of the supplementary videos. So we know to begin with that we want the slope in some cases to be less than 10%, right? So we know that's true. And I'm going to just be over careful and put everything in parentheses for when I want it to happen. So what this is going to create is a binary raster for everything that is less than 10%. And so when it's less than 10%, it can be that, and it needs to be north. And north is where aspect is, let's see, it'd be less than 67.5. I'm going to go check that for a second. So it has to be less than 67.5 because of the 0, right? There's this annoying 0. So 0 to 67.5 is north, but also 292.5 and greater is also north to 360. So I need both of those statements. So what I'm going to actually say is this is true or this is true, because both of them need to happen. So I'm going to say or aspect is greater than, oh gosh, 292.5, what was it? 292.5. 292.5. And so these two statements give me north, so I'll get a binary of 1 for north for that, a binary of 1 for north of that. The or kind of combines them together. And north is being intersected where slope is less than 10. Because if it's greater than 10, it's not okay. So we get the true value here intersected, or as an and statement, sorry, not or, but it's an and statement with this, which is north. So it's valid right now, but I think we also want to see the other statement, which is where slope is, we can just say less than 20. And we're going to say places that are south. And to get south, we need to do aspect is going to be greater than this number. But actually, we should do greater than or equal to, because if there is a pixel that is exactly 67.5, which there's probably not many, there are multiple decimal points. But if it's exactly that number, we want to include it as well. Less than this is an exclusive boundary. We want this to be an inclusive boundary because we chose an exclusive boundary there. So that'd be 67.5. And I know this is confusing as all get out probably, aspect is less than or equal to 292.5. So why did I use and that time? Well, because if I didn't use and I just said greater than and equal to 67.5, that would include this one, this one, oopsie, this one, this one, this one, this one, this one, and this one, up to 360. I don't want to include that, so it has to fulfill both statements. It has to be greater than this, and it has to be less than this. So that's going to create a selection that looks like this instead. So and is, again, requiring multiple things to be true, whereas or is allowing different things to be true. So I'm not done yet, though. I want this statement to happen as a unit, and so I'm going to put in my parentheses here. But then also, I want either of these statements to be true. So what I'm going to do is put them in brackets as well, like this. And I'm going to use the or. So it's kind of confusing, but I know that this statement is going to work because I've done this before. If you're confused about it, we can talk during office hours. Or you could run these all individually, and I'd be happy to go through it. I'm going to provide you with the buildable topography binary, though, so you don't need to worry about it. Okay, so I'm going to call this buildable. We call it terrain. I'm going to call it topography because that's really, to me, what it is. That's good. Buildable topography. It says it's valid. I'm just going to double check. Less than, or. Okay. All right, it ran. Let's see what it did. Yeah, that's pretty cool. So now what we're seeing is in as a 1 are places that our analysis says we're allowed to build, and 0 are places that we're not allowed to build or are impossible to build. So this is our constraints layer. And if you really want to kind of go and test it, let's just do that for a second. I'm going to make this semi-transparent just so I can kind of see. Apply. And I'm going to look at one thing at a time. So let's look at this random little spot here. So our aspect for that spot is, it looks like it's south facing, and the slope is, oopsie, the slope is just under 20%. That makes sense. So we've got a south facing slope, it's just under 20%. If I jump out of it, oh, suddenly we're in the 20s, and now it's over 20, it's no longer acceptable, right? And so it's kind of a fun way, I mean, it's really confusing to look at, but to go around and kind of test some places to see if our statements are true. It'd be great to find a north-facing slope and see as well. So I wonder if we can do that. Let's look for a north-facing slope, which I believe is red. So here's a north-facing slope. Here's a place where we have multiple things going on. So let's see. Yeah, okay, so this is north in this area. And so, let's see. Yep, it's 8%, 8%. Oh, we jump outside, boom, over 10%. It's under 20, but it's over 10. So I hope that's pretty clear that this tool ran. If it's not, like I said, talk to me at office hours and I can go over it. But I will provide you with this binary file, so you don't need to come up with that statement on your own. But I hope you can kind of see that the Raster Calculator is powerful. It can do lots of stuff, and you should use it. All right, the next video we're going to be intersecting this with our water constraints, so we can't build in places that are open water. See you in the next video.